This is I've seen this problem more than once. So I'm going to solve this. And I'm going to solve this for my classical mechanics class. And so that means I'm going to do things a little bit differently just in terms of the notation. I mean, it's still the same idea if you want to use this for an introductory course. But okay, let's just get to it. The idea is that I have a ball launched up an incline. So there's a plane inclined at an angle phi above the horizontal, and then the ball is launched with an initial velocity v0 and an angle theta above the incline. So it's like a projectile motion problem up an incline. That's kind of cool. And I'm actually going to solve this two ways. Okay, the first way is I'm going to say that this is my x-axis and this is my y-axis. And then the second way I'm going to solve this is to model this in Python numerically, and then just find out where it hits, and then just repeat that until I find out the maximum. I really want to find what angle gives me the maximum range. Okay, I didn't say that, so I'm saying it now. Okay, so let's start off the Newtonian physics way with this. F net equals ma. And I'm going to go through all the steps here because I care, and it's fun. Okay, so if this is my x and y axis, once the ball leaves, I have one force acting on it, the gravitational force mg. And you'll notice that in this, if I have my x-axis up the plane and my y-axis like that, this force actually acts partly in the x direction and partly in the y direction. Let me just draw that force, and this is my x-axis. That's my y-axis. This is going to be the angle theta, right? Because if, or is that phi? That's the angle phi. Yeah, that's the angle phi. That's the same as that, because that's how much my thing is tilted. If phi goes to 0, then this is just in the y direction. So that means I get actually two F net equations. I get one in the x direction. It's going to look like this. I'm going to have this x component of the force, which is going to be the sine of that angle, and then I have the y component of the force, which depends on the cosine of that angle. So I'm going to write that out. In the x direction, I get negative mg sine of phi equals mx double dot. And here I'm using this dot notation where x double dot is the second derivative of x with respect to time. And that's the way we do it in classical mechanics. We use this dot stuff because it looks cool. And then in the y direction, I have something similar, negative mg cosine phi equals my double dot. And the m's cancel in both those cases. Let's start with the x motion first. So I'm going to write this as x double dot equals negative g sine phi. I could write this as dx dot dt equals negative g sine phi. Now that's a phi. That's a phi. Now I'm going to multiply both sides by dt. So I get dx dot equals negative g sine phi dt. And in this form, I can integrate both sides. So if I integrate this side, I get x dot. So I have x dot as a function of t. Now I integrate this. G and sine phi are constants. So I get negative g sine phi. And then I have a constant. Now you'll see here OT. And the constant is going to be plus x dot 0. Because if I put in t0, then this term goes away, and this would have to be the velocity at t equals 0. I skipped a step there because I've done this in a previous video. All my classical mechanics playlist videos are in a playlist, the link's down below. So I could call that v0. So let's say negative g sine phi t plus v0. That's the x0. That's the x velocity. Okay, so now I can write this as dx dt equals negative g sine phi t plus vx0 dt. Now I can integrate both sides again. Oh, multiply both sides by delta t. And I get x as a function of t is this. I have negative g sine phi t is going to be t squared, and I have to divide by the 2. So I get negative 1/2 g sine phi t squared, and then I have a vx0, that's going to be vx0t plus vx0t, and then I'm going to have plus a constant, but again, I want this to be at t equals 0, I want that to be the initial position, so if I put t0, these two terms go away, so I just get plus x0. And that's my equation of motion in the x direction. Okay, let's set it up in the y direction. It actually is going to be almost the same thing. So here's, let's write down over here my x equation. So I'm just going to write it over here. X as a function of t is -1/2 g sine phi t plus vx0t plus x0. Okay. And then my y equation looked like this. -g cosine phi equals y double dot. So I can integrate once on both sides. I get y dot as a function of t. It's going to be -g cosine phi t plus vy0. Same idea, okay? Because it's the same equation. And then y as a function of t is going to be -1/2 g cosine phi t squared plus vy0t plus y0. So these are my two equations. Now let's do one more thing. If I look, here's my phi, here's v0, and that's theta. I want the initial x velocity and the initial y velocity. So this component right here is the x, and that's the y. So this is the adjacent side of that right triangle. So vx0 is going to be v0 cosine theta. vy0 equals v0 sine theta. So now I get the following two equations. X as a function of t, -1/2 g cosine phi t squared plus v0 cosine, wrong go, mister. I'm looking it up here. X as a function of t is -1/2 g sine phi t squared. I shouldn't have copied that down. That just threw me off in every single way. Plus v0 cosine theta t plus x0. That is important. And then y as a function of t is -1/2 g cosine phi t squared plus v0 sine theta t plus y0. Now, one important thing, notice what would happen if phi went to 0. Then I should get normal projectile motion, which has an x velocity as constant. So if this goes to 0, then in this case I have sine of 0 is 0. So this term goes away and I just get this. And over here I get cosine of 0 is 1. So you get your normal projectile motion equations. And that's one of the things you should always check, right? Does this reduce down to something that I already know? Okay, now what I want to do is to use those two equations. Let's just fold that over. I want to use those two equations, and I want to find out how far the ball goes up the plane. So let's draw the picture again. So this is phi, v0 theta. It's going to go like this. And I want to know this value right here, which is an x value. So let's pick this as our origin. So that means that x0 equals 0, y0 equals 0, x final, I'll just call it x, we don't know. And then y final, I do know, right? Because if this gets back down to here, that's where y is equal to 0. So if I look at these two equations, if I want to find the final x, -1/2 g sine phi is all stuff. I don't know the time. And here's another term. I know that, but I don't know the time. And I know that's 0. And then the y direction, I have this term, but I know the final y is 0, but I don't know the time. And the thing is that since this equation only has x's and t's and this has only y's and t's, these are two independent motions. And with that, that means that I can use the time from this and plug it into the time from up here. So what we want to do, and this is the same what you want to do with normal projectile motion, I want to solve this for time and then use that up here. Okay, so here, if I use my initial conditions of y0 is 0, then I get this. The final y is 0. 0 equals negative 1/2 g cosine phi t squared plus v0 sine theta t plus 0. So I can solve that for t. I can add this term to both sides. I get 1/2 g cosine phi t squared equals v0 sine theta t. Now I can divide both sides by t, and I get that canceling with one of those, and then I can divide both sides by this, and I get t equals 2 v0 sine theta divided by g cosine phi. Now with that, I can put this into my x equation. So for the time, I'm going to put in this time, and then I will get my x value. So let's do that. So I get x final is going to be negative 1/2 g sine phi. Now I have to put in t squared. So this is going to be 4 v0 squared sine squared of theta over g squared cosine squared phi. That's t squared. And you can check up here. I didn't do this. I should check this. Does this have units for time? Well, this is no units for the trig functions. Here I have meters per second divided by meters per second squared, so it does indeed give me time. So that's just a good check. And then I can put in my other term plus v0 sine theta times t, which is going to be 2 v0 sine theta over g cosine phi. Yep. So that's my x value right there. It's done. Okay. Now, can we simplify? Here's a g squared and a g. Here's a 2. And this has sine squared, and this has a v0 squared and a 2. Sine phi. We don't have similar terms. Well, let's do this. So what I want to do, that's my range. And we can just check, right? You can check, I know the range equation on level ground should only have one term. And so on level ground, phi would be equal to 0. So if phi is 0, then this term is 0. This whole thing goes away, and I get this, and that's 1. And this is the equation, the range, the official range equation. So that is good. Okay. But now I want to find the maximum range. So let's just, I want to know what angle of theta will this go the farthest. So I want to do this as a maximum problem. So I want to change theta. So any of the cosine phi terms I don't care about. So let's just see if we can rewrite this a little bit. X equals negative sine phi over g cosine phi. I'm just pulling all the non-theta terms out. V0 squared, there's a 2. That's that. And then I have sine squared theta. That's the part I care about. Over here, I get plus V0 squared 2 over G cosine phi, and then I get sine squared theta. So that's good. And right here I have, wait, they don't cancel. They don't cancel because this term's right here. But I do have, that's fine. Let's write, I only care about the sine squared theta. There's no other thetas in there. Is that right? No, there should be another theta in there. There should be, I made a mistake, because there's a theta right there. X equals, this should be cosine theta. I put time, and this should be cosine. So this is cosine theta sine theta, and that's correct. Okay, that's fine. Theta, theta, theta. Everything else is just a constant. So what I want to do in a classic Max-Min problem is to take the derivative of this with respect to theta and set it equal to 0. And then by doing that, that will give me the value of theta for the maximum or minimum x. And then we can find that value. Okay, so let's rewrite my function correctly this time. Now I'm going to write this as x as a function of theta. So let's just make sure we get it correct. X as this final x. It's going to be equal to negative 2 v0 squared sine phi over g cosine phi. I'm putting that all in parentheses because it's just a constant. Sine squared theta plus 2 v0 squared over g cosine phi times cosine theta sine theta. And that's in parentheses. Okay, so now technically it's a partial derivative. Let's take the partial derivative of x with respect to theta. I just want to know how it changes with theta. So this is a constant term, but this is not. So the derivative of sine squared theta, it's a power rule, so I have to bring the 2 down front. So I'm going to put, let's call this a, and let's call that b. They're almost the same. So I get 2a sine theta. But now I have to take the derivative of sine theta with respect to theta, which is going to be equal to cosine theta. And then I have to take the derivative of theta, which is just, this is with respect to theta, so it's just 1. So it's 2a sine theta cosine theta. Now for this one, I have a product rule. So I'm first going to take the derivative of cosine theta. The derivative of cosine theta is going to be negative b sine theta, and then take the derivative of theta with respect to theta is 1 times sine theta. And then I have to take the derivative of the other part, so I get plus b cosine theta cosine theta. The derivative of sine theta is cosine theta. Yeah. So here you get plus, so let's write this as 2a sine theta cosine theta minus b sine squared theta plus b, that's one plus, cosine squared theta. And we want to set that equal to 0. Okay, quite a problem here. We do need to use a trig function here, I think, because I want to solve for theta. And if this was plus, I'd have sine squared plus cosine squared, which is 1, but I don't have that. Let me just double check it if I wouldn't. So the derivative of cosine theta is negative sine, and I get that. And then the derivative of sine is cosine. So I get that. Okay, so what's sine theta, cosine theta? There is a trig identity. I can't remember what it is. I'm going to look it up real quick. Sine x cosine x. Sine x cosine x. Let's just do. You would think I'd just know all my trig identities instantly, and I don't. Maybe I could do a trig identity right here before I take the derivative. Trig identity. Here it is. Sine x cosine x, sine theta cosine theta is equal to 1/2 sine of theta plus theta, so 2 theta, plus the difference, which is 0. So that's that. So that is over here, but that doesn't really help me, does it? Oh, I've got myself into a pickle here, haven't I? Okay. I'm just trying to solve that equation, this equation right here. That I can replace, but then I still have a sine squared cosine squared. What if I did it up here before I take the derivative? I have a sine. If I replace that with that. Okay, I'm going to skip over to my other method to solve this. And then we'll see if it agrees, and then we don't have to worry about the trig identity. I know that's kind of like a cheat, but sometimes you just got to cheat, right? Sometimes it just happens. Okay, that's fine. Let me show you how we're going to do this numerically. So I'm going to switch back to my normal Cartesian coordinates. I could do it the other way, but then it'd just be the same thing. So I'm going to launch a ball with some angle. And in this case, I'm going to launch it with an angle V0 and at an angle at theta plus phi, right? Because this is the angle above the horizontal. I'm going to have this is my x-axis and that my y-axis. And if that's the case, it's normal projectile motion. I have x equals V0 cosine theta plus phi t. Right, and the initial x position is 0. That's my x equation. And then my y equation is going to be negative 1/2 g t squared plus v0 sine theta plus phi t. And then it starts at y equals 0. So this will give me the x and y position at any point in the future. And so what I want to do is say, where is it going to hit right here? And what is true about here? It's not x equals 0. It's not y equals 0. It's something else. So this is an equation. Let's say this is the equation y equals mx plus b, but it goes through the origin, so b is 0, so it's mx. So what's the slope of this line? So this is the angle phi. So if I take this side right here is going to be my y, and that's x. M equals y over x, which is the tangent of phi. So when x over or y over x is the tangent of phi, then it's back on this plane. So what I'm going to do is to model the motion of this in small time steps and then check, is y over x equal to tangent of phi? And if it's true, then it hit. And then I can find my distance, I'll call that s. S is going to be equal to the square root of x squared plus y squared, right? Because if you start here and you end there, how far is this? Well, I know x, I know y, that's the hypotenuse. So I'm going to do it one time, and then I'm going to do it, turn it into a function and do it a whole bunch of times. Okay. So if you're not familiar with Python, if you're not familiar with graphing, that's fine. Let's just get right to it. You'll pick things up, I'm sure. Okay, so here we are. I'm using GlowScript v Python. The first thing I'm going to do is to make a graph. G1 equals graph. And I want to, let's just leave it blank for right now. But I do want to put a width. Width equals 500, height equals 250. And then I'm going to make a graph. I'm going to just make two graphs. F1 equals G curve, color equals color dot blue. And then F2 equals G curve, color equals color dot red. And so F2, I want to plot that slope, and F1 is the trajectory. And then so I'm going to do that one time, and then I'm going to plot it, do it a whole bunch of times. And that's why I left that graph blank. So let's do F2 as the slope. So I'm going to say I need to pick some values here. Theta equals 20 degrees. I'm just picking stuff. I need to convert that to radians. Phi is equal to, let's say, 25 degrees. I need initial velocity. V0 equals 5. G equals 9.8. So I'm using the scalar value of G because I've already broken it up into a motion. I could do vectors. That's fine. We won't do that. Okay. And then I'm going to say T equals 0. dt equals 0.01. So now what I want to do is, I'm trying to think. I want to draw the line. Okay. So I'm not sure how far to make it go. So let's just say x temp TMP equals 0, dx equals 0.01, while x temp is less than 3. I'm just drawing the line. I'm going to calculate the y value for these x things and then plot them. So y temp is just going to be equal to tangent of phi times x temp. And plot that. F2 dot plot. X temp, y temp. Oh, why did I put the e there? That's kind of weird. It's not weird, it's just not consistent. And then I need to increase my x value. X temp equals x temp plus dx. Let's just see if that works. Straight line. Good. Okay. And this would be 25-degree angle if these are the scale's not 1-to-1, so that's fine. I probably should save this. Uphill projectile. Motion. Save. Okay. So what I want to do now, I'm thinking about my next loop for my time. I want to start with x equals 0, y equals 0, t I already have. And what I could do is something like this. While let's see, is it going to be greater than? Let's do this. Y slope equals x times tangent of phi. That's the equation of my line. So while y is greater than or equal to the y value of the slope, then do the following. And so that way I can go by just the y value instead of having to do the tangent value, calculate the tangent each time. Okay, so the first thing I want to do, well, I already know the equations of motion. I can just calculate x and I can calculate y. So let's just say x equals, I need this. Let's just write out v0 times cosine of theta plus phi. Remember, that's what I said. Times t. Y equals negative 0.5 times g times t squared plus v0 times sine of theta plus phi times t. So that'll just calculate my x and y values forever. Let's plot those. F1 dot plot x, y, and then I'm going to increase time. T equals t plus dt. And that should work. I should have that curve of a graph. It should be fine. Let's just see. Okay. So it didn't do it. It's way down here. Oh, maybe that's just because it didn't go very far. Let's increase the velocity, see what happens. So if I say the velocity of 15, still didn't go anywhere. Y slope is equal to x tangent of phi. Let's just do this, just to see if things are working. While t is less than 1 for 1 second. Okay, that worked. So that graph's weird. F2 dot plot, F1 dot plot. What happened to F2? Why is F2 all messed up? X slope is x tangent phi. Wow, I'm double losing on this problem, aren't I? Messing up both ways. What is wrong with this? What if I run this for 2 seconds? See, that looks fine, but why is that line not like down here? That's F2, the red one. Do I change F2.plot? dx, xtemp. What if I just get rid of this thing? And run that. Looks fine. Oh, -30. Ah! Ooh, it's going the wrong way. Why is it going backwards? X equals V0 cosine theta t. Y is -1/2 gt squared plus V0 t. V0 sine theta plus pi. It's the dumbest things. It's the dumbest things that you make a mistake on. That's fine. Let's put this back at 5. So what happened was I had my angle plus pi, so it was all the way over, so it was actually launching back the other direction, I think. Okay, so that looks like it's working. So let's go back over here and change this back to while y greater than or equal to y slope, and I made a mistake too. I do need to recalculate y slope. Y slope equals x times tangent of phi. Okay. Got it. Okay. So that's my final position. I could print that out. I don't really care. What I want to do now is to make a function that launches this at different angles until that value is the maximum. I'm actually just going to graph it, and I'm going to determine that. So let's make this whole thing a function. So if I do that, I'm going to go up here. I'm not going to plot anything right here. I'm not going to plot this. I want to make a function. And this function gives an angle of theta. That's it. That's all it does, and returns the value of s. So let's go up here. T equals 0. I can do it right here. Def uphill theta. And then I'm going to highlight this whole thing and indent it. And then up here, I don't want theta. That's fine. So, and then down here, I want to say return square root x squared plus y squared. And let's just see if this works. I had theta as 20, so I'm just going to say print s equals uphill 20 times pi divided by 180, and that should be meters. Let's just see if it works. Meters. So I'm running this function once with the same value. I didn't return that value before, but we should at least see if it kind of works. And it can't find it because I can't spell again. The classic case of me leaving off letters. Uphill. That's pretty bad. Okay, so I think it's working. Okay, so now what we're going to do is to, I have theta. I need theta. Let's do it down here. Let's make a graph. We're going to say the x label, x title is going to be equal to theta in radians. Let's change it to degrees. And the y title is going to be equal to range in meters. And so that way I can plot the range as a function of theta, and I should be able to see which theta gives me the best value. So down here, I'm going to get rid of that. I'm going to say t theta equals 0. I'll start at 0. I don't really care. D theta is, let's say, 1 degree. I'm going to go by 1 degree increments. So I'll say 1 times pi divided by 180. And now what I'm going to do is say while theta is less than 90, times pi divided by 180. I don't know why I did that. Do the following. Calculate the range. So I'm going to say S equals uphill, and this should be t theta, temp theta, uphill t theta. So t theta is going to return a value. And so now I have it as S. I don't even need to do that though, but I did. And now I'm going to plot that. So I'm going to say f1.plot the angle, which is going to be t theta, times 180 divided by pi. So now it's back in radians. I mean, it's back in degrees. S. And now I'm going to increase my value of theta. So t theta equals t theta plus d theta. And then I'll do it again. So this should produce a graph of the range as a function of theta, and we should be able to find, let's save it, the maximum angle. Okay, so I think that worked. Weird stuff happened over here. That's fine. Basically, I think maybe it's going backwards. Not sure what's going on. It went back down. This is weird. But over here, you can see I get a maximum range of 32.6 degrees. Maximum range at 32.6 degrees. Okay, let's go over here and let's just say def C range and input my angle theta. And I'm going to use the equation that I had before because I didn't know what it was. So let's just see if that is correct. So I'm going to type in this. A equals -2 times v0 squared times sine of phi divided by g times cosine phi. That was my A term. B I had was 2 times v0 squared divided by g times cosine of phi. So now I can just return the value of the range based on theta. So let's say S temp is going to be equal to 2 times. Oh, that is it. That was x. I didn't want. That was x as a function of theta. Let's just do that. So this does return the range, not the derivative. So it's just going to be b times sine of theta squared plus, I'm sorry, that's A, plus b times cosine theta times sine of theta. Return S temp. Okay, and then I'm going to say print 32.6 range equals, return, look at that. Typo problems today. Return C range 32.6 times pi divided by 180. Let's just see what happens. Okay. So I get a range of 1.86 and 1.8. Oh, I have 32.2. Okay. So I think it's close enough. That tells me that the equation that I wrote probably is legitimate. Okay. And I just had a problem taking derivatives and using trig functions. But overall, I think I've explored this problem well enough. There's another way to solve this problem. There's multiple ways to solve the problem. I want to do it with the derivative. I just got stuck in the trig function. So there you go. I'm going to stop there. I'm going to give you the code for this problem down below, and also a link to the playlist for my classical mechanics problems down below.